So, hello and welcome to this lesson. And this happens to be our fifth lesson in our study of mathematical biology 2. So, in this lesson, we will be talking about population, the Lotka-Volterra model, okay, or the predator prey model, which falls under population dynamics of interacting species, okay. So far, we've been discussing population dynamics of single species, where we talked about the Malthusian model, the logistic growth model, and the harvesting in population model. So in this video, we'll be talking about when we have two species interacting, okay, and we'll be starting off with the Lotka-Volterra model or the predator prey model. So before we dive into the model, let's just take some definitions. So first of all, we'll talk about a predator and get to know what a predator is, alright? Because this model is going to be between predators and preys. So when you talk about a predator is any population species which feeds on another species for survival. Okay. And when you talk about a prey is a population species which serve as a source of food to other species, mostly to predators. So now let's take examples of some predators and their prey. So for instance, we have fox and rabbit, right? So fox feed on rabbit. We have the hawk and the chicks. We have sharks and herrings. And we can talk about the four armyworm and cereals, example like maize, okay? So all these are predators and they are prey. So when you have an interacting population, right, of predators and their prey, how can we study their population, right? So that's what Lotka and Volterra did, alright? So the Lotka-Volterra's predator prey model is an example of a model to describe population dynamics in interacting species. So we have three of them, right? The other two are competition model, and we can talk about mutualism or symbiosis. So all these are some introduction. I hope you are getting it. All right. So named after the Italian mathematician Vito Volterra and the Austrian chemist, demographer, ecologist, and mathematician Alfred J. Lotka. The Lotka-Volterra model describes the interaction between a predator, right? So example, sharks with population Y of t and its prey. Example, herrings with population S of t. Okay, so in this model that we are going to describe, we are going to mostly represent the predators with sharks and the prey with herrings, okay, but it works across. So Lotka-Volterra considered three situations for the two population species. Alright, so we have two population species, right? We have the preys and we have the predators, right? So the predators feed on the prey. So in the absence of the predators, that's the sharks, I told you in this video are going to mostly refer to the predators with sharks and the prey herrings, okay? So in the absence of the predators, it is assumed that the rate at which the prey grow is proportional to the number of prey at that time, right? And that's true. The predators feed on the prey, and when they feed on the prey, they reduce their population. That means in the absence of the predators, the prey are going to outgrow, and mathematically we can have the x dt is proportional to x, meaning the x dt is equal to some constant times what x, alright? And you can see that this here is the Malthusian growth model, right? So that means the absence of the predators, the prey are going to grow exponentially. And that's equation one, okay? where lambda is the per capita growth rate of prey, which is constant. So that's the first case. Okay, so we consider a second case. So in the absence of the prey, the predators will die exponentially. Okay, because the predators feed on the prey. So that means that if the prey are not around, the predators are not going to get much food to eat or nothing to eat, and as a result they are going to die. So that's the rate at which a predator dies or goes extinct is proportional to the number of sharks or predators present at that time. So if we let y of t be a population of the predators, then we will have dy dt will be directly proportional to y, right? And when we introduce a certain constant minus mu, right, then equation 2 holds. So note that equation 2 we have negative because of the death, right? For the equation 1, in the absence of the predators, the prey were going to grow exponentially. So that means that the lambda, which happens to be b minus d, will be greater than 0. So it will be positive because the birth will be more than the deaths. But in the case of equation 2, mu, which is equal to b minus d, will be less than 0 because the deaths will be more than the birth. Alright? Okay. So that gives us equation 2. So when mu is a per capita death rate of sharks, and then minus sign because the population reduces. Okay. So the third case we can consider is in the presence of herrings and sharks in the sea. So when the two of them are all present in the sea, what will happen? So the population of the herrings will be reduced by bxy, where b is the rate at which the shark eats the herrings and the xy is just the two population interacting, right? So in the presence of the two, the predators are going to feed on the prey. That means that the population of the prey will reduce and that of the predators will increase. So in the second case is that the population of sharks will increase by cxy, where c is the rate at which the sharks produce new offsprings as a result of feeding on the herrings. Okay, right. So when we add these terms to equation 1 and equation 2, that will give us the following system of what ODEs, and which is known as the Lotka-Volterra model, right? So you can see that in the absence of the predators, we had dx dt is equal to lambda x, but when they interact, right, the population of the prey, they are going to reduce, right, by minus bxy. So and that of the predators are going towards increase by cxy. Okay, so these equations are what we call the Lotka-Volterra Predator Prey model. All right, I hope you get it. Okay, so after getting this system of equation or this system, right, one thing I have to know is that we have to analyze it, but we can't solve this system of equations analytically, right? But we can obtain some information about the behavior of its solution, and we would like to use phase plane analysis, right, to analyze the model. But to make things very simple for us, we would first want to non-dimensionalize the equations. Okay, so you could see that when you take these two equations, we have lambda b mu and what c. We have 4 parameters, and we want to non-dimensionalize it to reduce the number of parameters. Okay, and also to make the equation very simple. So in non-dimensionalizing it, we are going to consider these equations. So we are going to let u be equal to c over mu x, and v be equal to b over lambda y, and tau will be equal to lambda t, and alpha will be equal to mu over lambda. Alright, so take a critical look at this equation, because those are the equations we are going to use to non-dimensionalize the system. Okay, right. So when we take the first system, it is dx dt. The dependent variable here is what, x, and we want to change x to what, u, right? So that means we have to write a chain rule in terms of what that. So that means we have the x dt will be equal to the x du times the u d tau times the tau dt, right? So you can see that when we try to cancel, we are still going to end up with the x dt. Then we have u is equal to c over mu x. From this equation, I told you to take very good care of them, like a very good look at them, because we'll be referring to them a lot, right? So from u equals c over mu x, we'll have x will be equal to mu over c times u, right? So we have to find the x du. So when you find the x du, we are going to get mu over c, and from here we have tau is equal to lambda t. So when you find the tau dt, we'll get lambda. So when we substitute them into this, we are going to get the x dt will be equal to mu lambda over c times the u d tau. And we call that equation 3. Alright. So when you put equation 3 into equation 1, this equation 1, so wherever you find the x dt, we put this there. Okay. Alright, so sorry, let me so we have to make that substitution. So when we put equation 3 into equation 1, right, we are going to get mu lambda over c du d tau. The whole of this represents the x dt to be equal to lambda x, but now x is what? Mu over cu minus b. The whole of this is now x, and the whole of this is now y, from the equations that we wrote earlier. Okay, right. So when we get here, lambda will cancel lambda, and also cancel the lambda here. Mu will cancel mu, also cancel the mu here, and c will cancel c, right? So we are going to be left with the u d tau will be equal to mu minus, and b will also cancel b. So u minus uv, right? The u d tau will be equal to u minus uv. And from here we can factorize u out, and we'll get the u d tau will be equal to u times 1 minus v. So this happens to be the non-dimensionalized equation for the first equation, right? So from the second equation, we have the y dt equals minus mu y plus cxy. And from the equation that we wrote down, we said v is equal to b over lambda y. So making y the subject, we get y will be equal to lambda over b v. When you find the y the v, we are going to get lambda over b, and the tau dt will give us lambda, because tau is equal to r lambda t. Okay, alright. So when we make substitution into this equation, we are going to get the y dt will be equal to lambda squared over b the v the tau. And we call this equation 5, and we have to put equation 5 into equation 2. So wherever you find the y dt, we put lambda squared over b the v the tau there. Okay, so putting equation 5 into equation 2, we'll get lambda squared over b the v the tau will be equal to minus mu, but now the whole of this is y, the whole of this is n, the whole of this is y. Alright, so one of the lambdas here will cancel this, and it will also cancel this, and b will cancel b. Okay, so we'll be left with lambda d v d tau will be equal to minus mu v plus mu uv, and this is the same as lambda d v d tau equals mu uv minus mu v. Alright, and we can factorize mu v out here, and we get lambda d v d tau will be equal to mu v u minus 1. And when we divide through by the lambda, we'll get d v d tau will be equal to mu over lambda v times u minus 1, right? But in the equation we wrote, we said alpha is equal to mu over lambda. So we can make that substitution, and that will give us d v d tau will be equal to alpha v multiplying u minus 1. That's going to be the non-dimensionalized equation for the second equation, right? So that means that now our non-dimensionalized models or equations are what we can see here. So we've been able to non-dimensionalize the original equation, which were like this, to what we can find here. I hope you get that. All right. And you can see that now, instead of having four parameters here, now we only have one, that is alpha. So that means analyzing this is going to be very simple as compared to the original one. Okay, so that's the reason why we non-dimensionalized. So we are going to use phase plane analysis, right? So we are going to divide equation 1 by equation 2. Okay, so we are dividing equation 1 here by equation 2. So when we do that, so that is equation 1 divided by equation 2. And when we do that, we are going to get the u div will be equal to u times 1 minus v over alpha v u minus 1, right? And when we decide to do rearrangements, we are going to get alpha u minus 1 over u. The u will be equal to 1 minus v over v in the v, right? Then we can bring the alpha out and integrate both sides, right? So u minus 1 over u is the same as u over u minus 1 over u du, and 1 minus v over v is the same as 1 over v minus v over v. And when we simplify further, this is the same as integral, because u over u is 1, integral 1 du minus alpha integral 1 over u du equals integral 1 over v dv minus integral 1 dv, right? So when we integrate all of them, when we integrate what we have here, we are going to have alpha u of tau, because u is a function of tau. Then this will give us minus alpha ln u of tau plus existing arbitrary constant will be equal to ln v of tau minus v of tau, right? So when we make c the subject, we are going to get this, and we let a certain function, a function of u of v, be given by the c. Okay, so now when we get here, what we do is that we find critical points. So to find critical points, we have to set del f del u to 0 and del f del v to 0. So when we find the partial derivative of f with respect to u, we'll get alpha over u minus alpha, right? Because this is f of u then. So when we differentiate this partially with respect to u, we'll get alpha over u minus alpha equals 0. And this is the same as, which implies that alpha minus alpha u equals 0. And this implies that, I think it's mu, or it's u. Okay, I think it's u. Right, so this implies that u is equal to alpha over alpha, which is 1. Okay, and when we also find del f del v, we are going to get 1 over v minus 1 equals 0, and that's 1 minus v equals 0, and we get v equals 1, right? So hence 1 1 is a fixed point, right? So after getting a fixed point, we would want to know the nature of the fixed point, right? Whether it is a maximum or it's a minimum. So to do that, the Hessian matrix is going to help us. You're going to use the discriminant of our Hessian matrix. So this is our Hessian matrix, and the discriminant of it is just going to be the determinant, which will be the product of this time this minus this time this. Okay, but note that by the Cleric rule, this is the same as this, right? So that's the reason you can see f of u v squared here. So when we find the second derivative of our function f partially with respect to u and u itself again, we are going to get minus alpha over u squared, and with this one we are going to get minus 1 over v squared. Okay, so that is, we take this and differentiate this again partially with respect to v, and we take this and differentiate it again partially with respect to u. So they are going to give us what we can see here. No. Okay. So it will give us what we can see here. And when we take the partial derivative of what we can see here, are going to get 0. So when we put it in this relation, we will get the discriminant d will be equal to minus alpha over u squared times minus 1 over v squared. That will give us alpha over u squared v squared. So at the fixed point u star v star, we are going to get, when you put 1 here, it will be alpha over 1 squared times 1 squared, which will be equal to alpha. So you get a discriminant to be what? Alpha. But alpha is a positive parameter, so alpha is greater than 0. So since d is 0, it means that the fixed point is either a maximum point or a minimum point. So we have to find out which of them it is, right? So to find out that it is maximum or minimum, then we have to find the del squared f del u squared, right? So when you find that one, are you going to get minus alpha over u squared? Alright, so at the fixed point u star v star equals 1 1. This will give us minus alpha over 1. So that means you are going to get minus alpha, which will be less than 0, since alpha is positive. Alright, so because it is negative, it tells us that the fixed point u star v star equals 1 1 is a maximum point. If it was positive, it would have been a minimum point. Okay, so now we know that the fixed point that we found, u star v star equals 1 1, is a maximum point. So this is the interpretation. The fixed or critical point u star v star equals 1 1 gives the maximum number of herrings and sharks in the sea, right? So that gives the maximum number of herrings and sharks in the sea. So do you remember we had f of uv equals ln v of tau plus alpha ln u of tau minus v of tau minus alpha u of tau, right? So at the maximum, that's f max, right? U is 1 and v is 1. Okay, so when we put that into our system, we are going to get ln 1 plus alpha ln 1 minus 1 minus alpha times 1, which will give us minus 1 minus alpha, which will give us minus multiplying by 1 plus what? Alpha, right? But if you could recall, alpha was given to be mu over lambda, so we can see f max is equal to minus mu over lambda plus 1, right? So this is the maximum point, right? So that was by using the fixed plane analysis, right? So we can also do fixed point analysis. Okay, so with the fixed point analysis, if you could recall, these were our non-dimensionalized equations. So we are going to let whatever we have here be equal to f of uv, whatever we have here be equal to g of uv, right? So to find a fixed point, we have to put the u, the tau, and the v, the tau to 0. When we do that, we will get u minus uv equals 0, u times 1 minus v equals 0, which implies u is 0, or 1 minus v is 0, which implies v is equal to 0. And in the second one, we are going to get alpha v u minus alpha v equals 0. So alpha v multiply u minus 1 equals 0, which implies that v equals 0 or u equals 1, right? So that means we are going to have the fixed point 0, 0, and 1, 1. So we are going to discuss the stability of these fixed points. So the Jacobian matrix is given by del f del u, del f del v, del g del u, and del g del v. So we have to know what our f is and what our g is. So this is our f, u minus uv, and this is our g, alpha v u minus alpha v, right? So when we take del u, del f del u, it is 1 minus v. Del f del v is minus u. Del g del u is alpha v, and del J del V is alpha u minus alpha. So now you have to take the first fixed point. So at u star v star equals 0 0, when you put 0, like wherever you see u, put 0, wherever you see v, you put 0, you will get 1 0 0 minus alpha, right? So when you find a fixed point, the eigenvalues of this Jacobian matrix, you are going to get 1 and minus infinity. Okay, so since at least one eigenvalue, that is lambda 1, is positive, it means that u of tau and v of tau grow exponentially. So that fixed point is linearly unstable, right? So that means that the fixed point 0 0 is linearly unstable. And what this implies is that when you have a small amount of herrings and a small amount of sharks, a small amount of predators and a small amount of prey, they are going to grow, right? And it's going to make the system unstable. So now at the non-zero fixed point 1 1, right? When you put 1 u equals 1 here and v equals 1 here into this that we have, you're going to end up with what you can see here. So g of 1 will be equal to 0 minus 1 alpha 0, right? And when you find the fixed point of this system, right, and the eigenvalues of this Jacobian matrix, we are going to have this here, and this is going to give us lambda 1 lambda 2 to be plus or minus root of alpha I, right? So you are going to get complex roots. So it implies that u star v star equals 1 1 is a center singularity, saying the eigenvalues are purely imaginary. And it means the solution will be of the form. So when we are solving system of ordinary differential equations, right, the solution is always of this form. So you can see that when you bring the proportionality here, then that means that our c1 v1 and c2 v2 go away, and our lambda 1 lambda 2 now are what we can see here, our root of alpha I and minus root of alpha I, right? Okay, so one thing is that this system has a period or seasonality that occurs at t equals 2 pi over root of alpha, but alpha is given by mu over lambda. So that means that it has a period t equals 2 pi over root of mu over lambda. And there's the interpretation. Okay, so the period is proportional to the square root of the ratio of the linear growth rate mu of the prey to the death rate lambda of the predators. So even though we are only dealing with small perturbations about the steady state, u star v star equals 1 1, we see how the period depends on the intrinsic growth and death rate, right? So for example, an increase in the growth rate of prey will increase the period, and a decrease in the predator death rate does the same thing. So what we did was we have herrings and sharks in the sea, all right? And the sharks feed on the herrings, the predators feed on the prey. Okay, so we first discussed the relationship between them and how to get a mathematical model, right? And we got that, and we analyzed the mathematical model, right? And we want to know the period where we are going to have bumper harvest of the herrings, and we said that that period is given by 2 pi over root of mu over lambda. And we are saying that the period where we are going to get a bumper harvest of herrings is going to depend on the linear growth with mu of the prey and the death rate lambda of what mu, which is the death rate of the predators, and the death rate of the predators, which is mu, right? So Okay. All right. So that means that when there is an increase in the growth rate of the prey, it will increase the period, right? And when there is a decrease in the death rate, it does the same thing. That means that if more herrings are born, right, the period where we are going to have a bumper harvest increases. And if more of the sharks die, that means that they will not feed on, there won't be much sharks to feed on the herrings. So that's also going to increase what the period. Okay. So that's it with the predator prey model and the lot, and that's the Lotka-Volterra model, right? So thank you very much. In our next video, we'll talk about competition model. Okay.